Alright, here's the video for Chapter 9. Chapter 9, so Chapter 7 we talked about light and electrons and how they behave. In Chapter 8 we talked about how electrons are around different elements or in different elements. And then in Chapter 9 we're going to start dealing with how chemicals bind to each other. And what we're going to learn about is the Lewis model of chemical bonding. And the Lewis model is very important because it's very predictive about how things bind. And so for the Lewis model though, like what we discussed in class and what's very important with the Lewis model is what's known as the Lewis structure. And so the Lewis structure, let's say you take the elemental symbol, so in this case carbon, and we know carbon has 4 valence electrons because it's in the 4th column. And so we can put 4 dots around the elemental symbol because there's 4 valence electrons. So each dot is equal to 1 electron. And so Lewis structures are very, very important in this chapter. There's 3 different types of bonds that are described in Chapter 9. We're going to just talk about 2 types. The first type is the ionic compound, or the ionic bond. And so the ionic compound, the Lewis structure can describe this bond, but that's not why Lewis came up with it. And so when we start talking about covalent structures, we'll see the true power of the Lewis structure. But for now, we'll look at ionic compounds. So we know ionic compounds are between a metal and a non-metal. And so let's take sodium and chlorine. So the Lewis structure for sodium is that there's only 1 valence electron, and for chlorine it's this. And so we know an ionic compound is between 2 different ions. So what's going to happen is this electron is going to be stolen, quote unquote, from the chlorine, leaving us with a sodium plus 1 because it lost its electron, and a chlorine minus 1 because it gained an electron. And obviously these 2 things come together to make sodium chloride. We can also do sodium oxide, where oxygen has 6 valence electrons and sodium only has 1. So when the oxygen removes 1 electron, it still has a spot open. So the way we fill it is with another sodium. And so here we have Na2O. And so that's sodium oxide. And so ionic compounds, right, this is how we get the subscripts. It's based on the number of electrons that are transferred. And the Lewis structure does show this. So why do we care about ionic compounds then? We care about ionic compounds because ionic compounds are very exothermic. The formation of a lattice or of a solid salt is very exothermic. However, if it was just about making the ions, so for sodium, if it was just about doing this, we would get up to step 4. And as you can tell, this is a plus, this is a plus, this is a plus, this is a minus. So we have 3 pluses to 1 minus. If it was just about making the ions, you would get a positive delta H. So it would be endothermic. But I told you that it's very highly exothermic when you form an ionic compound. And the reason for that is because of this step right here. It's known as the lattice energy. Right? So the lattice energy is the energy that is given off, or that is emitted, when 2 ions come together to form this solid lattice. So, why am I showing you this? So I'm showing you this because this is a theoretical cycle for how we form ions. You do not have to know how to calculate delta H naught of F. It would be through Hess's law where you do step 1 plus step 2 plus step 3 plus step 4 plus step 5. and get to the end. But what you should be familiar with is this right here. Is that the equation that describes lattice energy is the ions in the gaseous state going to their solid compound, right? And so the two ions have to be in their gaseous state, and this equation describes the lattice energy. And so you should be familiar with that. The actual math on how to calculate these things, not so much, but you do have to be with the theory. So, this is just with ionic compound, right? So this is a brief overview. The Lewis structure came to ionic compounds, but what the Lewis model and the Lewis structures really can show us is covalent compounds. So, let's look at an example of this. So 59A. So 59A, we want to do the Lewis structure for this, Ci4. Now, we know covalent bonds are usually between two nonmetals. And so here is Ci4. So we come to the list of rules that I have given you guys on the Canvas site, asked you to print it out. We just need to do as much practice as we possibly can until we get these rules secondhand, until we can just look at something and then make a Lewis structure for it. Step number 1 is we're going to calculate how many valence electrons we have. So in carbon, there's 4. In iodine, there is 7. But we notice with the iodine, there's 4 moles of it. So what we need to do is multiply these 7 valence electrons times 4, which will give us 28 total valence electrons for the iodine. But the total number of valence electrons for this whole compound is the valence electrons from iodine plus the valence electrons from carbon. And so we have 32 total electrons. Alright, so step number 2. We need to now draw the skeletal structure. And so the way we do that is we use single bonds. But before we even put single bonds in, we usually put the least electronegative element in the center. In this case, we'll talk about electronegativity in the next slide or in the next couple slides. And so for now, just know that carbon is the electronegative. The other rule that you'll see on your list in number 2B is that usually the first element listed in a compound goes in the center. There is an exception with hydrogen like H2O, but this case it's carbon, and so then it says we need to bond with using single bonds. Now, single bonds, single bonds equal 2 electrons apiece. So here we have 4 single bonds, so that's going to be 8 electrons. So we're going to take 32 minus 8, because we've already used 8, and that's going to give us 24 electrons. And so since we have 24 electrons, the next step, step number 3, is to determine how many electrons you have left over after single bonding, and then start filling in lone electrons around all the elements on the edge. So in this case, it'd be the iodines. And we want to fill octets. Remember, the goal of the Lewis model is to make sure each element has 8 electrons. And so we said this bond is worth 2 electrons. Well, so let's count to make sure we've used all our electrons. So we have 6 around this. 6 times 4 is 24. So we don't have any electrons left over. So we've used up all our electrons. Then the step is we want to make sure that we have octets for everything. So for this iodine, we have 2, 4, 6 with the bond that makes 8. Same thing with this iodine, and this iodine, and this iodine. This carbon has 4 bonds. 1, 2, 3, 4. Because of that, it also has 8 electrons, because each bond is worth 2 electrons. And so we are done. This is the final Lewis structure for Ci4, for carbon tetraiodide. Before we go on and look at another one, I want to just quickly bring up, there's two different types of pairs, of bonding, or of electron pairs that we're going to talk about. Here's one type of pair. This is known as a lone pair. Right? Lone pairs do not participate in bonding. They are usually on the outside of elements. We'll talk about a little bit more where lone pairs can go in Chapter 10, but for now we just need to know there's lone pair. This right here, this bond, is known as a bonding pair. Bonding pairs go, or bonding pairs are pairs of electrons that actually participate in bonding. So, let's look at so for class on Friday, I want you guys to do number 59, B, C, and D. I want you guys to do those just to practice, to get, again, familiarize yourself with Lewis structures. So let's look at another compound. This will be number 54. So here we have CH2O. So this is number 54A. Alright, so carbon. So let's do step number 1, valence electrons. Right, so hydrogen has 1, we multiply it by 2, so there's 2. Oxygen gives us 6, carbon has 4, so this is going to be 12 total electrons. So, the one we'll put in the middle is carbon, because it's the most electronegative. We'll put H's on the bottom and oxygen to the right. Wherever you put that oxygen, it doesn't matter. We want to try to make it as symmetrical as possible. So we're not putting all three in like one area. So then we bond them with single bonds. We've used 6 electrons. So you have 6 electrons left. So remember, hydrogen only needs 2 electrons. So one bond to hydrogen will fulfill its needs. And so here we've used 6 electrons filling the octet for oxygen. We have no electrons left. But we have a problem. And the problem comes in with that carbon. Take a second and just count the electrons around that carbon. Alright, so if you've counted, you know that there's 6 electrons around that carbon, not 8 that it needs. So what we're going to have to do, since there's no more electrons to put on this carbon, what we're going to have to do is we're going to have to take a lone pair from the oxygen and form a double bond. Right? So there can be more than just a single bond. So in this case, we're making a bond. And so now everything, if we count it, everything will have their octet. Oxygen has 2, 4, and then 6 and 8 from the bonds. Carbon has 2, 4, 6, 8 from the bonds. And then hydrogen just has 2 from the bonds. And that is perfect. That is the Lewis structure for CH2O. So for practice, I want you to try number 53, B, C, and D. And these will also be due on Friday. Again, the more practice that we get, the better we'll get at it, the more it'll become second nature. So, we're talking about covalent bonds. Not all covalent bonds are equal, right? There are things called polar covalent bonds, right? Polar covalent bonds use this table of electronegativity to determine which element will more likely have the electrons around them than the other. So they share them, they just don't share them equally. So fluorine up here at the top right is the most electronegative element. And so as you go down a column, you decrease electronegativity. As you go across from right to left a row, you decrease in electronegativity. Whereas fluorine is the most electronegative, which means all the electrons will go towards fluorine. And so what will end up happening, let's get hydrofluoric acid here. So what will end up happening is these electrons tend to move towards the fluorine. There's still a covalent bond, but it's an unequal sharing. And so when that happens, fluorine kind of gets a negative charge, whereas hydrogen kind of gets a positive charge. This is known as a dipole moment. The moment that these elements are partially charged. It's not fully charged. Fluorine isn't negative and hydrogen isn't positive. It's not an ionic compound or an ionic bond. It's just a semi-positive, semi-negative. We can draw an arrow like this, where the cross is for the positive side, the arrow points towards the negative, right? And so the electrons are shared more with the fluorine than with the hydrogen. And so it's very important that we remember these electronegativities, because what we're going to do is we're going to talk about formal charges, right? Because the two covalent bonds we talked about earlier, there was nothing, those were it. That was it. Those were the structures. There's no other structures. But some compounds, like let's say NO3 minus, maybe have one or more different compounds. And so let's look at that. And so NO3, okay, so we have 5 from nitrogen, 6 from oxygen, but we're going to multiply by 3, so that's going to be 18 for a total of 23 electrons. Now, there's something that we have to account for, and what we have to account for is this. So NO3 minus is an ion. Because it's an ion, because it's an ion, we have to either add or subtract an electron. Since it's an anion, negatively charged, we are going to add an electron. It's a little backwards to what we are used to and what we want to do. We want to subtract that. But instead, we're going to add on to it. So, we now have 24 electrons. Nitrogen is the least electronegative. We're going to start with single bonds. So there's 6. We have 18 electrons left. Let's fill the oxygen octets. And so now we have used 18 more electrons. We have no electrons left. Just like the previous example, our nitrogen does not have an octet. So let's take this pair and make it an octet. So we're going to erase our housekeeping or bookkeeping. Just going to draw this up here. So we have this. Okay. There's it there too. Okay. So there's this. But couldn't I also draw it like this? And the answer to that question is yes. I could also, if I wanted to, draw it like this. So, these are known as resonance structures. Resonance structures do not change the atoms in the molecule. It just changes the way they're bound. So as you can tell, the double bond is here to the right, or up, or to the left. The same molecule, same NO3 minus, it's just the way that that double bond is formed is different. That's the resonance structures. So, how do we determine which resonance structure is more likely? Well, we do what's known as determining formal charges. So, formal charge is the charge that each individual atom or element has in a compound. So, how do we determine formal charge? Well, on the handout I gave you, the bottom 3 rules help us determine formal charge. So, the first thing for each formal charge is we count each bond as 1 electron. Right? So if you have a double bond, you have 2 electrons. If you have a triple bond, you have 3. So everything has its octet. So we're not worried about octets now. Now we're counting formal charge. So what you do is you count the number. Whoop. Oops. That's better. So what we do is we count. There we go. Don't know what happened there. So what we do is we count the number of bonding electrons for each element. We count the number of lone pairs, or lone electrons, right, the ones that are non-bonding, and then we add them up. So let's look at this oxygen first, right? So it's got 2 bonding electrons, and it's got 4 lone pairs, for making a total of 6 electrons. Now, let's think about these oxygen, right? So if we look at oxygen in the Lewis structure, it'll look like this, with 6 electrons. Well, this oxygen matches this oxygen with the number of electrons, so there's no charge. Let's check this nitrogen. So, this nitrogen has 4 bonding electrons, 2 from the double bond and 1 from the single, another one from the single. The lone electrons, there aren't any, and so it has 4. Now let's look at nitrogen's Lewis structure. It has 5. And so we're missing an electron. When you miss an electron, you become positively charged. And so here's a positive charge. If we look at this oxygen, so let's go back over to our table. That oxygen has 1 bonding electron and 6 lone electrons for a total of 7. But down here we said oxygen has 6, so it has an extra electron around it, which means it has a -1. And these 2 electrons are the same, so we have a -1. So +1, -1, -1, 0 gives us a total charge of -1. Now there's 2 ways you can denote charge on an ion like this, and you will have to. One of the ways is this, where you just put the formal charges on each element, and then that's good. The other way is we can put brackets around our structure and put a -1 on the outside, denoting that the whole compound has a -1 charge. And so, to practice this, to practice calculating formal charges, I want you guys to do number 69 for Friday. So I understand this is a lot of practicing doing Lewis structures, but it'll be really good practice to help you guys for the quiz that'll be on Friday, as well as drawing all these Lewis structures. So the last thing we're going to do. So we've been telling you with these Lewis structures that everything needs an octet. However, there are some exceptions to the octet rule. 1, odd electrons. So we should just be familiar that there are some things that just don't have a full, even amount of electrons. So let's look at NO2. So NO2 is a greenhouse gas, and it's actually very reactive. This is what it looks like. Right? It's just got 1 sole electron on its nitrogen. This is known as a free radical because it's unpaired. Whenever you have 1 electron on an element in a compound, it's known as a free radical. And so this free radical, right, is very reactive because it wants to pair up with its electron. And so one of the things, so odd electrons, I will not probably give you odd electron species on an exam or a quiz, just because sometimes they're just really strange. The other one is incomplete octets. So let's look at this. Boron trifluoride. So boron trifluoride, let's do what we did before. So I will tell you this is the way boron trifluoride looks. Now, when you do this, you will think, oh, I need to do a double bond. So let's do a double bond. So we're going to have B double bonded to an F, bonded to an F, bonded to an F. So, remember when we talked about formal charges? Let's count the formal charges of this molecule. So fluorine has 7 valence electrons. 1 for the bond, and then here 6 for the valence. So this is plus 0. This is plus 0. Here we have 1, 2, 3, 4, 5, and 6, right? The one with the double bond has 6 electrons. That means it's a plus 1, because it doesn't have 7, it has 6. So it is a plus 1. This boron usually has 3, and here we have 4. This is a minus 1. I want to ask you guys a serious question. How much do you think that fluorine wants to be a plus 1? Because it's the most electronegative molecule or element on the periodic table. It doesn't. So we don't want to do that. So here we have 0, 0, 0, and the boron is 0. Since everything is 0, there's no formal charges, that's fine. So boron can have an incomplete octet. We can also do what's known as expanded octets. So what expanded octets mean, you can have something bound to more than 4 different things. This is not carbon. Carbon cannot be bound to more than 4 different things. And so what this includes are things in the 3rd row. Things like phosphorus, sulfur. Arsenic is a little bit lower, but arsenic can still be in there. Xenon, iodine, right? And so the question is, why? Why can these have an expanded octet? And the reason is because they have a d orbital. So right now, phosphorus does not fill its d orbital. However, it is available just in case they want to put something in there. So just to let you guys test this, I want you to do number 75, A and B. I know I'm not going to give you an example of expanded octets, but I just wanted to see if you guys can do it. You look in your book, maybe come to me and ask for some help if you need it. But I want you to do number 75, A and B for Friday. So I understand, like I said, that's a lot of things for Friday. But it's really good practice. It's really good time to go through everything and just get really good at Lewis structures. The last thing we're going to cover, and I apologize for the length of this video, but the last thing we're going to cover is bond energy. So there's one other way that we can calculate delta H of the reaction. And that is the sum of the bonds broken. Since now we're going to look at how things are actually formed and made, plus the sum of the bonds formed. So I will tell you, this number will always be positive, this number will always be negative. So, let's look at a reaction, number 83 in your book, to see how we can use this math to calculate delta H of the reaction. So we're going to have carbon solid plus 2 H2O gas goes to 2 hydrogen gas. If you notice in your book there is a typo. They do not balance this equation. So let's think about this. Right? So we know bonds broken plus bonds formed. The bonds formed are going to be negative. The bonds broken are going to be positive. How do we know the energy within a bond? It is in table 9.3 You will not have to memorize it. I will give you, if there's a question like this on an exam or a quiz, I will give you all the information you needed like I did before. So, how many bonds are in carbon solid? No bonds, right? It's a solid metal. We're not going to talk about it. There's no energy on the table. We're not going to worry about it. Plus, if we do the Lewis structure of H2O, we know it's this. Well, we know we have 2 moles of this, so really we have, let's do a different color here, orange. So we have 2 OH bonds plus, or times another 2, so this is going to be 4 OH bonds going to, we know hydrogen is just this, so we're going to have 2 H bond H, and then we're going to do plus CO2. CO2 is this. And again, I'll give you a practice problem to do so you can practice making your own Lewis structures in this context. And so we know we have plus, and there's going to be 1 bond, 2 double bonds, 2 C double bond O. And so now what we can do is we're going to start plugging in the equations, right? So we have 0 plus 4 times the OH bond, which is 464. This plus 2 times, and remember, bonds formed are negative 436 plus 2 times negative 799. So let's go ahead and erase this. So this is very similar to when we did the delta H naught, when we did the delta H of the standards of formation. So what we get is on the left, we get 1856. I'm just going to go ahead and do a minus in front instead of a plus, a minus. And what we have is 872 plus 1598. So we have 1856 minus 2470. And that is going to equal, I don't know why I did the arrow. And that is going to equal negative 614 kcals per mole. Or kilojoules. Sorry, this is in kilojoules. So, what type of reaction has a delta H of a negative number? That's right, exothermic. So, exothermic reactions form stronger bonds than are broken. So they form stronger bonds than are broken. So an endothermic reaction would break stronger bonds than are formed, leading to a negative or positive. And you can tell that by these numbers way down here. You can already tell whether something's going to be endothermic or exothermic. And so I would recommend looking at that. So, for practice, and you guessed it, for Friday, I want you to try number 81. Try number 81 for Friday. So you have a lot of practice to do before Friday. It'll be good. And so I hope you guys, if you have any questions, please come and see me.